Patient HM, the single most studied brain in the history of neuroscience. At a young age, HM cracked his skull in a bike accident and began developing seizures. Despite high doses of medication, HM suffered through years of severe epilepsy and eventually dropped out of high school. HM's diminished quality of life led him and his family to seek help from one of the most renowned neurosurgeons at the time, who removed a small area of the brain where the seizures were taking place. The operation was a success, and the seizures virtually disappeared. But here comes the unexpected bad news. HM was no longer able to form new memories. He could recall memories from his childhood and remembered how to speak the English language, but even though neuropsychologists would visit him every single day, they always had to reintroduce themselves because he never recognized them. HM's story may remind you of a different patient population with memory impairments: Alzheimer's disease. At least 50 million people worldwide are living with Alzheimer's or other dementias, and every 3 seconds, not 3 minutes, 3 seconds, someone in the world develops dementia, and it has no cure. The hippocampus is especially vulnerable to damage from Alzheimer's, and symptoms include wandering and getting lost. A person with Alzheimer's may not remember their name or address, which is why they often wear a medical ID bracelet around their wrist. But before we're able to fully help individuals with hippocampal damage, we need to know how the normal hippocampus functions. My research investigates the brain mechanisms that underlie the formation of new memories. What exactly are brain cells, also known as neurons in the hippocampus, communicating? Neurons are incredibly tiny. Therefore, I had to design and construct a device with microwires thinner than a strand of human hair. Next, I surgically implanted the device into the rat's hippocampus and listened to the activity of individual neurons as the rat freely explored. Interestingly, whenever the rats visited specific locations in space, different neurons would increase the frequency of their activations. These neurons, termed place cells, preferentially activated when rats occupied specific place fields within space, and taken together, hippocampal cells form a cognitive representation of the world. For example, if a rat experienced a novel event, some place cells changed their activation patterns, suggesting the neurons processed new information and updated their representation of the world. To date, prior researchers have primarily focused on the part of the hippocampus that's easier to target with microwires. The novelty to my PhD thesis is I'm simultaneously targeting both easy and difficult to reach areas because there's evidence suggesting different areas may serve distinct memory functions. The ultimate goal is to build a model of how healthy brains create new memories, to form a necessary basis for developing medical interventions, and to help people with memory impairments like patient HM. Thank you.